Most fighters are small, fast, and built to turn on a dime. The Tupolev Tu-128 Fiddler wasn't. It stretched almost 100 feet, weighed more than 40 tons, and looked closer to a passenger jet than anything you'd expect in a dogfight. So why did the Soviets call the Fiddler a fighter at all? The answer takes us to the Arctic. Endless, empty skies where American bombers could slip past Soviet defenses. And to patrol that space, the Fiddler needed engines powerful enough to carry a monster across half a continent. By the late 1950s, the Soviet Union faced a unique problem. Its northern borders stretched across endless Arctic wilderness, far from dense airbase networks. American bombers armed with nuclear weapons could fly through this space, and smaller Soviet fighters like the MiG-21 simply didn't have the endurance to stop them. The Soviet Air Defense Force needed a new kind of interceptor, something that could patrol for hours, carry a large radar, and also fire long-range missiles. Tupolev, famous for its bombers, was tasked with building it. The result was the Tu-128. But for such a huge aircraft, ordinary engines would never do. Engineers chose the Lolka AL-7F2 turbojets, proven in other aircraft but adapted for very different roles. These engines gave the Tu-128 its reach, its speed, and its unique identity. The Tu-128 was powered by two Lolka AL-7F2 afterburning turbojets. Each engine produced around 22,000 pounds of thrust, or 98 kilonewtons with afterburner, giving the aircraft a combined thrust of over 44,000 pounds. The AL-7F2 had already been used in the Sukhoi Su-7 fighter bomber, but Tupolev engineers adapted it for long-range interception. This meant focusing on endurance and reliability as much as sheer thrust. These were large axial flow turbojets with 9 compressor stages, an annular combustion chamber, and variable exhaust nozzles. At full afterburner, the roar of the engines could be heard for miles, and the Tu-128 accelerated past Mach 1.5 despite its size. Each engine on the Tu-128 was nearly the size of an entire early MiG fighter. Together, they turned a massive interceptor into a machine capable of racing across the Arctic skies. But power alone wasn't enough. Those engines had to survive Arctic cold and supersonic heat. So let's look at how they were built. The AL-7F2 engines were built with Soviet metallurgy that had to handle enormous stress. Compressor blades were made from high-strength steel alloys, optimized to handle long patrols in freezing conditions. Turbine blades used nickel-based alloys designed to withstand extreme exhaust temperatures. Combustion chambers were annular, spreading heat evenly to reduce hotspots. Soviet engineers emphasized ruggedness over finesse. The AL-7F2 was not as light as some Western engines, but it could handle the harsh conditions of Siberia without frequent replacement. Anti-icing systems were integrated into the intakes, channeling hot bleed air over the lips to prevent frost from forming. Without this, the Tu-128's engines could choke on ice crystals within minutes of flight in Arctic winter. The Tu-128 was never exported, so its engines had to work reliably under Soviet maintenance alone. Strong metals were one thing, feeding the core was another. Supplying air to the AL-7F2s required huge lateral intakes along the fuselage. These intakes were designed to capture enough airflow at both subsonic patrol speeds and supersonic dash. Variable guide vanes controlled how air was delivered to the compressor, preventing stalls. Fuel was equally critical. The Tu-128 carried nearly 20 tons of kerosene in multiple tanks spread through its fuselage and wings. Pumps and transfer systems constantly moved fuel to maintain the aircraft's center of gravity. Without this balancing act, the interceptor would have been unstable as its massive tanks emptied. At full throttle with afterburner, the Tu-128's engines could burn through around 500 kilograms of fuel per minute. That meant a supersonic interception dash was measured in minutes, not hours. But at cruise, the AL-7F2s were efficient enough to give the Tu-128 a combat radius of 1,500 kilometers. Think of it this way. The Tu-128 was essentially a flying fuel tank wrapped around 2 giant turbojets. Testing the Tu-128's engines revealed challenges unique to its mission. Intake icing was a constant threat in Arctic air. Engineers added heating ducts to keep airflow clear. Compressor stalls occurred during sharp throttle movements at high altitude. Pilots were trained to advance power smoothly. Heat stress on turbine blades required frequent inspection. Soviet mechanics became adept at swapping blades before cracks spread. Despite these issues, the AL-7F2s earned a reputation for reliability. Unlike more temperamental engines of the era, they rarely failed in patrol conditions. That reliability mattered more than agility because the Tu-128's job was to loiter for hours before unleashing a short burst of supersonic speed. The AL-7F2s gave the Tu-128 remarkable performance for an aircraft of its size. It could reach a top speed of Mach 1.6 at altitude and climb to a service ceiling of about 60,000 feet or 18 kilometers. With full fuel and missiles, its combat radius stretched to roughly 1,500 kilometers, while in ferry configuration it could cover nearly 3,000 kilometers without stopping. These numbers put the Tu-128 in a league of its own. Smaller fighters could outmaneuver it, but none could stay airborne as long or cover as much ground. Pilots described the engines as steady at cruise and forceful in afterburner. At full power, the Tu-128 accelerated smoothly despite its weight, but they also noted how quickly the fuel gauges dropped during supersonic runs. The engines of the Tu-128s weren't working alone. In fact, they were part of a carefully balanced system. The Interceptor carried the Smerch radar, one of the largest ever fitted to a fighter. It could detect bombers at long range, guiding the Tu-128's R-4 air-to-air missiles. Those missiles were heavy and draggy, meaning the engines had to provide enough thrust to carry both the plane and its weapons load. This integration meant the Tu-128 wasn't a fighter in the traditional sense. It was a system with radar, missiles, and the engines all working together. The AL-7F2S were the muscle behind it all, ensuring the Interceptor could carry heavy loads without losing supersonic ability. But every supersonic run fought the physics of temperature. Running giant turbojets at supersonic speeds creates enormous heat. The AL-7F2s faced exhaust temperatures exceeding 1,700 degrees Celsius in afterburner. Without advanced cooling, turbine blades would have melted within minutes. Soviet engineers used several solutions: hollow turbine blades with internal cooling channels, nickel alloys that resisted creep and cracking under stress, thermal coatings that reflected heat away from vulnerable surfaces. Even with these measures, maintenance teams had to replace blades regularly. The Tu-128's engines were tough, but they paid a price in durability every time afterburners were engaged. But endurance was the real weapon, and the tanks had to feed it. Fuel defined the Tu-128's role as much as its engines. With nearly 20 tons of kerosene on board, the aircraft could patrol for hours. Fuel pumps constantly balanced the load, shifting kerosene between tanks to maintain stability. Engineers even designed redundant pumps, ensuring the engines would never starve mid-patrol. At cruise, the AL-7F2s were relatively efficient, burning a fraction of their maximum fuel flow. But once the afterburners lit, consumption skyrocketed. At full power, the Tu-128 could drain over a ton of fuel in just a few minutes. This is why pilots used afterburner sparingly. The engines gave the Tu-128 range, but they also demanded respect. A commander had to plan every dash carefully, knowing fuel burn would limit how long the fighter could chase intruders. The Lolka AL-7F2 engines powered the Tu-128 from its introduction in 1964 until its retirement in the 1980s. They were not revolutionary, but they proved that scaling up existing designs could serve unique needs. The Tu-128 was eventually replaced by the MiG-31, whose engines were more efficient and more responsive. Yet without the AL-7F2s, the Soviet Union would never have fielded an interceptor capable of patrolling its vast northern borders. The legacy of these engines lives on as a reminder that sometimes endurance and reliability are just as vital as speed and agility. The Tu-128's engines were not perfect, but they made possible the largest fighter jet ever built. The Fiddler remains history's largest fighter, and its Lolka AL-7F2 engines were the heart of its story. And that raises the bigger question: what other machines push the limits of size and power in aviation? The F-35 is not just another fighter jet. It's a multifaceted beast that combines stealth and design. The strongest fighter jet in America's arsenal started off as a bold idea: one jet that could replace many others, fight in the air, and even hover like a helicopter. So how was the F-35 designed to dominate the skies? Let's break it down. In the 1990s, America faced the problem of its aging fleet. The F-16 Fighting Falcon was fast but not stealthy. The FA-18 Hornet could fight from carriers but lacked range. The AV-8B Harrier could hover but was unreliable. And the A-10 Warthog was great at close air support but too slow for modern air combat. The Pentagon wanted one jet that could do it all. Thus, the Joint Strike Fighter program was born. The result would be 3 versions of the F-35. F-35A, conventional takeoff for the Air Force. F-35B, short takeoff and vertical landing for the Marines. F-35C, carrier variant with larger wings and reinforced landing gear for the Navy. The challenge wasn't just making a new fighter, it was making a single airframe adaptable to 3 different missions, which was something no one had done before. And at the heart of that vision was one critical component. At the core is the Pratt & Whitney F-135 engine, the most powerful fighter jet engine in service today. It produces 43,000 pounds of thrust, nearly double what powers an F-16. The F-135 is a low bypass turbofan with afterburner. First, a 3-stage fan pulls in about 400 pounds of air per second, roughly 180 kilograms per second. Next, a 6-stage compressor packs that air to about 30 times normal atmospheric pressure. Fuel is added and burned in the combustor at around 2,000 degrees Celsius. The hot, expanding gas drives the turbines at about 10,000 revolutions per minute, and what's left is accelerated out the nozzle to make thrust. Hit the afterburner, and raw fuel is sprayed directly into the exhaust, igniting in a secondary flame that pushes the F-35 to Mach 1.6. That's not as fast as the F-22 Raptor's Mach 2.25, but the F-35 trades top speed for stealth and versatility. For the F-35B, the engine connects to a lift fan, which is a vertical fan behind the cockpit, powered by a shaft from the engine. It produces 20,000 pounds of thrust downward. At the same time, the main nozzle swivels 90 degrees and small roll ducts balance the jet. Unlike the Harrier, which blasted hot exhaust straight down, the lift fan uses cool air, reducing heat damage to decks and improving stability. Now here's a question for you. How much vertical lift can the lift fan system generate in total? Drop your guesses in the comments and we'll answer this one in the outro. What good is power if you can be seen? That's where stealth engineering comes in. The F-35's shape is designed to scatter radar waves. Its fuselage blends smoothly into the wings with no sharp right angles to reflect radar. It has canted tail fins, the inlets are S-shaped to hide the engine face, and the exhaust nozzle is flattened to reduce radar and heat signatures. The entire jet is coated in radar-absorbing materials. These layers soak up or scatter radar energy. Even the canopy is coated with a thin layer of gold, bouncing radar while letting the pilot see clearly. Weapons are stored internally in bays. Carrying weapons on wings creates radar reflections. So, in stealth mode, the F-35 carries 4 missiles or bombs hidden inside. In beast mode, it can carry 22,000 pounds of weapons externally, but at the cost of stealth. These stealth decisions make the F-35 nearly invisible to radar. In combat exercises, F-35s have scored kill ratios as high as 20-to-1 against older jets. The F-35 had to be light, tough, and heat-resistant. A near-impossible combination. Engineers solved it with advanced materials. 35% of the jet is titanium, forming its backbone and tolerating high heat and stress. 42% is carbon fiber composite, which is lightweight yet incredibly strong. The rest is aluminum and other alloys. Thermal coatings reduce infrared emissions. Even the paint is engineered to resist heat buildup while remaining stealthy. The airframe was also designed for maintainability. Unlike the F-22, whose stealth coating requires long repairs, the F-35's composite skins are easier to replace and maintain. The result is a jet strong enough to withstand carrier landings but light enough to maneuver and stealthy enough to hide. If the F-135 is the jet's heart, the sensors are its brain. The AN/APG-81 Advanced AESA radar can track dozens of targets simultaneously and jam enemy radars. It can even map terrain with incredible precision. The distributed aperture system uses 6 infrared cameras around the jet to give the pilot complete 360-degree coverage. With the F-35 helmet, the pilot can see through the jet, viewing infrared video as if the jet were transparent. The electro-optical targeting system adds laser targeting and infrared search, and is built seamlessly into the nose. All this data is fused by onboard computers and projected into the pilot's helmet display. There's no need to look at multiple gauges. Everything like the radar tracks or threat warnings is presented as a single picture. Older pilots say it's like moving from black and white television to high-definition streaming. The F-35's internal bays hold two AIM-120AM RAM missiles and two 2,000-pound JDAM bombs in stealth mode. Smaller diameter bombs allow even more capacity. Externally, pylons can carry Sidewinders, JSON cruise missiles, and heavy ordnance. The F-35A includes an internal 25mm GAU-22 cannon, firing 3,300 rounds per minute, while the B and C versions use an external pod. This flexibility allows the jet to shift roles instantly. Stealth assassin one day, bomb-laden strike aircraft the next. But no weapon matters without the ability to control the aircraft itself. The F-35 is inherently unstable by design. This instability gives agility, but it requires a fly-by-wire system where computers make constant micro-adjustments to keep it smooth. The jet's software runs millions of lines of code, which is more than any commercial aircraft. It integrates flight controls, radar, sensors, and weapons into one system. For the F-35B, hovering is computer-assisted. The pilot doesn't need to manually balance thrust. With one button, the jet hovers. The system automatically adjusts lift fan, nozzle, and ducts. This engineering choice of using digital control instead of manual complexity made vertical flight practical for everyday pilots, not just specialists. But even the most advanced code needs to be proven in the real world. The F-35 underwent 8,000 flight tests before full production. The Arctic trials proved the engine could restart at -40 degrees Celsius. The desert trials showed it could fly through sandstorms in 50 degrees Celsius heat. They also conducted hover trials, which demonstrated that F-35Bs could transition from hovering to supersonic flight in under 8 seconds. In combat, Israeli F-35s have struck Syrian targets undetected. USA's F-35s have flown missions in Iraq and Afghanistan, integrating seamlessly with older jets. Critics argue about cost and maintenance, but its battlefield performance proves the engineering works. But to really understand what makes the F-35 different, you have to look at where the pilots sit. Step inside the cockpit and you'll notice something unusual. There's no traditional head-up display. For decades, fighter pilots relied on a HUD to project speed, altitude, and even targeting onto the canopy glass. The F-35 throws that out entirely. In its place is the helmet-mounted display system, a $400,000 piece of engineering that turns the pilot's visor into a full panoramic screen. Every piece of information is projected directly onto the helmet. Using the distributed aperture system, the pilot can literally see through the jet, with infrared cameras projecting live video beneath their feet. Wherever the pilot looks, sensors and weapons follow, allowing them to lock and fire simply by aiming their eyes. Each helmet is custom molded to the pilot's head, ensuring the displays are perfectly aligned. This philosophy reduces workload and increases awareness. Instead of juggling dials and scopes, the pilot sees one fused picture of the battlefield. For the F-35, information itself is the ultimate weapon. The F-35 story begins with the X-35 prototype built by Lockheed Martin. The X-32 had a large, ungainly intake and struggled with vertical flight. The X-35, in contrast, successfully demonstrated short takeoff, supersonic dash, and vertical landing in a single flight, and it was the first jet ever to do so. That win secured the Joint Strike Fighter contract. Lockheed Martin partnered with Northrop Grumman and BAE Systems, while Pratt & Whitney built the F-135 engine. The program ballooned to over $1.5 trillion projected lifetime cost due to delays. Yet despite criticism, the F-35 is now the most numerous fifth-generation fighter with over 1,000 delivered. Now let's answer that question from earlier. The lift fan system makes 40,000 pounds of vertical lift, which is enough to raise the 30-ton jet off the ground. The F-35 Lightning II proves that it is more than a fighter jet. It's the most ambitious engineering project in aviation history. If you enjoyed this breakdown, like and subscribe for more deep dives into the world's most powerful machines.